All right, welcome back. So we talked about the explore task last time. Now I want to talk about the other performance task, the create task. Okay, so remember, okay, 40% of the grade in the AP CS Principles exam is the create and the explore task. 40%. That means that you can really help your students get a 5 by focusing on this and making sure that they get all the points they can muster out of this. Okay. Bad news, performance task is done during class time. I mentioned that you need to devote 2 weeks to the explore task. You also need to devote 2 weeks of class time to the create task. That is a month that is taken out completely. Okay, and that doesn't include practice runs. So if you do want to do 2 explores, 2 creates, so you can give them feedback, well, then might be 2 months that gets lost. On the upside, no free responses during the exam. This is your students' best chance to really kind of load up on points. And then maybe if they lose some during the multiple choice, you're still looking at a 5. So I really like the performance tasks. This is the timeline we talked about earlier in respect to the explore task. So with create, I like to do it at the beginning of the spring semester. Okay, make sure to get plenty of time for this. By that time, they had a whole semester of programming, so they're really capable and they can build something interesting. They don't actually have to turn it in until the end of April, but I want them to be ready at least by the beginning of April, so we can put this behind us and move on. Okay. All right, the create task. What are they going to do? They're going to write a program. Okay. What kind of program? Anything that they want. Okay. Again, let me emphasize this. Do not tell them, write this program. Okay. Do not tell them, oh, you know, maybe in the SNAP curriculum, in the BJC curriculum, there are some for you to explore later, right? Pick one of those. No, I mean, let's actually, hopefully it'll be something that they're interested in and they're building. Sometimes they bring ideas from other classes. Like my son actually did a physics simulation because he was learning physics at the time, was kind of obsessed with orbits. So boom, right? There is a perfect create task, right? An orbit simulator. So whatever they choose is okay. I will talk about some caveats, okay? But generally speaking, we want them to pick what they want to do. We do not want to give them a project to do. They just don't bring the same enthusiasm, the same energy to it that you want. Okay. Now, the other thing that the College Board wants you to do is not just write a program, but also to think about the process of writing a program. The process of writing a program. Okay. And I'll talk more about that later. But we're actually going to ask them to kind of reflect on how I wrote this program. Okay. They need to be able to recognize algorithms, right? Somewhere in that program that they write must be a sufficiently interesting algorithm to highlight, okay? So they need to be able to think about it and say, here it is, this is my best algorithm so far, okay? Boom, that needs to happen. If they say, I can't find an algorithm in my program, they pick something that's too easy. We need to push them a little to actually make something more interesting, okay? They also need to find an abstraction. Right? Abstraction is all over computing. Somewhere in their program, they must have consciously used abstraction. They must have created an abstraction, not just used an abstraction somebody else designed. Actually create their own abstraction. And they need to be conscious of it, so they can say, right here is the abstraction I built. So those are kind of the pieces of a good create task. Okay. So what makes a good program? It has to be simple enough that the student can actually write it, okay? They actually have to write some program. So if they say, yes, I'm writing this thing that's gonna control all the satellites and make sure that, sounds fantastic, great, I love it. I love it when they push themselves. You got 2 weeks, okay? You're not going to finish that program. So I don't wanna be here next week at the end going, are we ready? No, I'm still kind of no. This is a disaster, okay? So don't let them get too big, okay? The goal is not to write the most impressive program to kind of just absolutely floor the AP readers and have them go, how can a kid write something this complicated? No, okay? The goal is just to write a program. So don't get carried away. Don't let your students get carried away, okay? It does, however, have to have a good algorithm and a good abstraction. So it has to be complex enough for that, right? For example, if you're running a game, games are great. A lot of students actually pick games as their program. Maybe you should have collision detection, right? It has to have something in there that they can point to and go, see, right here, interesting algorithm, right? Sometimes it's embarrassing. It's like, oh yes, every time that we touch this, the score goes up by 1. That's my algorithm. That's too simple. Okay, that's just counting. That shouldn't actually be an algorithm. So we have to kind of direct them a little better, because like I said, this is really an opportunity to get 40% of the points. You hate for them to lose half the points in the create task because their algorithm is not really an algorithm. Okay, so be careful. And again, it has to have a good abstraction. Right? My litmus test for good abstraction is a subroutine, right, or is a block that they built. Right? I'll get to that. Okay, so not only do they actually have to write a program, they have to record a video of the program running. Okay, now the chief reader for this exam makes the point, and I really like this point, that the video is the only evidence the readers have that the student succeeded in writing something that worked, at least partially, at some point in time. Okay, it's possible that after they got it to work like that, they added some more code and broke it, right? It's possible. It's possible then to get the entire program running, they only got this one thing and they had this big vision. Okay, that's possible. Okay, but still something ran, right? And that's really the point of this video. It's just the evidence like that. So I had the opportunity to watch this video where a very, very excited student looked at us in the camera and actually, had some very, very artistic video. There was a pool, there was just beautiful outdoor scenery and lots of stuff, and told us how great the program was, and told us, how much it meant and how wonderful it was to write it. Oh, and APCS Principles was the best class in high school, and it was all very exciting. And at the end of that, we went, and where is the program that you wrote? Okay, we never saw it running. Sorry, right? No points. Okay, we never saw the program running, so we can't give it any points. Sometimes students will take screenshots. And here is the first level of my game. Here's the second level. Here's the third level. Isn't it great? I'm sure it is. But I didn't see the program running. All I saw was screenshots, right? You can fake screenshots, right? There doesn't have to be anything running in the background. So how do I know that your program ran? That's not good enough. Screenshots are explicitly ruled out. It has to be a video that shows the program running, okay? So actually show the program running. Some students send the code. This is my program. Okay, technically they're right, but that's not what I want to see. I trust you that there's a program. I want to know that it runs. Hit the button that says run, and then show me how the program is actually running. Okay, so that's what we're looking for. Again, you got 60 seconds. That may not be enough to do the whole program. And some of them, honestly, after 48 seconds, we, the readers, are trying to turn off the thing because it's like, okay, we got it. It's a Pac-Man clone. Still a Pac-Man clone. Still a Pac-Man clone. Does anything else happen? Nope. Still a Pac-Man clone. So if it's 15 seconds, that's okay too, right? You've shown me what I needed to know, right? You can't run over 60 seconds. For some programs, that's just not enough time to show all the features. So don't. Just show me something. I need to see that something runs, okay? That's the goal of this video. Okay, so now we have the prompts that we have to answer, right? Question 1, upload the video. Question 2A, you really need to tell me what the program is, right? You could have done that in the video via narration, right? I don't trust that because sometimes the audio gets corrupted. Lots of things go wrong. And if we can't hear it when we're grading, it's not there. We can't grade it, okay? So I like having a backup. Just in question 2A, tell me what it is. So one thing the College Board really, really asks for is what language did you use? Okay, so if they use Snap, we use Snap. Okay, actually say that somewhere. Don't leave it up to people to kind of guess by looking at the way your program works. Okay, actually tell us. We use Snap, we use Python, we use Java, whatever. Okay, just say what language you used. Okay, mention the purpose of the program. Again, this is the purpose kind of in a general sense. So if you write a game, it's okay to say this is to entertain people. Okay, that's the purpose of the game. I don't know why, but another kind of very popular create task is a Quizlet type application that actually asks you maybe words in English versus French. Okay, the purpose is education to help people memorize things, right? Whatever it is, just say this is what my program is trying to do. The purpose is not what the program does, okay, is why does the program do it? So for example, the purpose is not, I'm running around chased by 4 ghosts, right? That's not the purpose. The purpose is entertainment, okay? What actually happens in the program? I run around chased by 4 ghosts, right? That's why I'm entertained. But actually answer, why did we write this, okay? And then, remember, you uploaded a video that showed the program running. Tell me what was happening in that video. So for example, the program might be something to help me keep track of the collection of books that I have in my house, okay? What you showed might be just adding a book to the collection. Tell me that, right? In the video, I showed you how you can add a book to the collection. The program also lets you search for books and stuff like that. Okay, great, great. At least I know the one thing that you showed me. The next question, 2B, is about the process of programming, okay? There's quite a few points here to be had. You have to understand how to fill out this form correctly. So the first thing that you want to show is that it is an iterative process. Here's what the College Board does not want to see. I came in, I wrote my program, I was finished. It took 10 minutes. Okay. They really don't want that, right? They want to see, it took me 2 weeks to write this program, right? I came in several times. In fact, they explicitly look for at least 2 different times that you describe in the answer to this question, right? Maybe when you started writing it, when you're in the middle, when something came up, okay? There needs to be 2 separated instances instances of time that you can identify and talk about, okay? Part of the way that the College Board helps you is by asking you to describe a challenge and or an opportunity, right? Actually, 2 of those, right? I prefer to have like 1 challenge and 1 opportunity that's actually not written into the rubric. It could be 2 challenges, 2 opportunities. Still, I go with a safe one. 1 challenge, 1 opportunity. That's what the rubric used to demand. So might as well stick to that, okay? So what kind of challenge might you have? It might be a bug that was really difficult to fix. It might be a feature that was very difficult to implement, okay? Those are the kind of challenges that you want. Now, there is some wiggle room as to whether a challenge can be, and then I didn't know what the program should do, so I had to really think about what I wanted to happen, right? Yeah, that's a challenge. You can technically say that is, requirement solicitation, which is a part of developing software. That's gonna be very dependent on who's reading, who's actually grading that particular solution. So don't, okay? That's not a good challenge. A better challenge is, I couldn't get this to work, okay? Perhaps sometimes this would happen before that, sometimes it would happen the other way, and because there were 2 things that were happening at almost the same time, but not quite, there was a problem that was really hard to fix. Beautiful, right? They want to see that, okay? Opportunity. This might be something as, so as I was writing the code, I really wanted to be able to have objects, bounce off each other. So I needed to figure out how to make them bounce. And then I remembered that way back in the previous semester, we had a homework assignment that just did bouncing off the edges of the screen. And I thought, oh, maybe I can use that same code as an opportunity. Brilliant, okay? Use something like that, okay? How do you solve your challenge? How did you solve, or how did you take advantage of your opportunity? Again, that's part of the response to this question. Here's what they don't want to see. I couldn't get this program working, so I asked my friend Sam. Sam looked at it and went, oh, it's because you didn't add the right kind of variable. It's local and it should have been global. Thank you, Sam. No, they don't want to see that, okay? They don't want to see, I had this problem. Oh, this could get you in big trouble. I asked my teacher, and my teacher helped me. That is academic dishonesty, okay? Because they're submitting this, and somebody actually helped them do it. You can actually get help from your peers. You cannot get help from adults like your teacher, okay? My dad helped me figure this out because my dad knows how to program. Academic dishonesty, you are in big trouble at that point. The entire create task is lost. Maybe even the entire exam is lost, okay? So don't do that, okay? How did I solve it? What the College Board wants to see is me, myself, and I, okay? It was hard. I thought a lot. I figured it out, okay? That's what the College Board wants to see. If that's not true, it's okay to say, Fred helped me, Sally helped me, okay? But somewhere in there needs to be something that you did yourself, right? The student did all by his or herself. The College Board is looking for that. So one litmus test that I use is when I read the response, there must be places that say I, right? As opposed to we. We sat down and discussed this. We decided that the best way to solve it was like this. We remember that we did this, right? That sounds like it's a team effort, okay? I don't know what you did in this team effort. I can't give you credit. So make sure your students understand that. I sometimes feel bad for the student who uses the royal we or the editorial we in principle, right? This is not the place to do it, okay? You must be able to say what you did by yourself, okay? They used to look for the word individually, right? That's a little too much, right? Although it's okay for the student to just be explicit and say, I wrote this by myself. Great, okay, that takes that fear out of the way, and then they can focus on what they actually got done. Okay, prompt 2C, that is about identifying the algorithm that was used. Okay, so this is really hard because an algorithm can technically be as simple as x equals x plus 1, add 1 to x, okay? That is technically an algorithm, it's an instruction that needs to be followed. That's not the kind of algorithm that the College Board is looking for, okay? So there must be something that is big enough to count as an algorithm. So what do we mean by big enough? That's hard. So the College Board has tried many times to actually address this. What it's come down to is the following. It must have at least 2 different parts, okay? So the algorithm can't just do one thing. It has to take something else and combine it. Okay. Now, why is that important? So that it's complex enough, right? If the whole thing is just like this and you can't break it into smaller parts that make sense, it's probably too small to be a big enough algorithm, okay? So they do want to see that it's kind of split into at least 2 parts, okay? The parts must work independently, right? So you must be able to describe each part. It's not like this is the first half and this is the second half, right? They must be able to work independently. You should be able to describe exactly what each one of them does. And then you need to say how they combine to do your new result, your algorithm, okay? Now, another way of measuring kind of how complicated it is that it has to at least have sequencing, right? What does that mean? Do this and then do that. So it's got to have at least 2 lines. It can't just be 1 line of code. It's got to be 2 lines of code. It's not asking for a lot, right? But it's got to have 2 lines so that it does this and then that. It must have to make a decision. That's called selection. If this, then do this, else do that. Okay? It must have selection or an if statement. Okay? It must also have iteration. It must have some loops. Okay? For each element, do the following, right? Again, that's not a hard and fast rule. Okay? As long as you have 2 parts that are somehow connected and independent and combined, you probably can get all the points if you argue it well enough. But I tend to feel that you don't want to be at the mercy of the reader. You actually want to force the reader to give you full credits, okay? So go ahead and use something that has sequencing and iteration and selection. More than 1 statement, an if statement, and a for loop or a while loop or something, right? It should also have some math, okay? It doesn't have to be a lot of math, but it should have something in there that looks like A plus B times C. That's all we're talking about here, right? There needs to be some arithmetic operations, right? Alternatively, there needs to be some logical operations. If this happened or that happened, that counts as math, okay? But you want to have some kind of operations, right? So it doesn't have to be real complex, but it really should be the heart of your program. That's what you're kind of putting a spotlight on. So since it is the heart of your program, hopefully it's complex enough. Otherwise, you pick the program that's too simple, right? So again, that's what you got to tell your students. Make sure they don't mess this. By the way, some teachers go to the AP reading, they learn about the rubrics, and then they go back and use that in what they tell their students. So I actually graded this thing where a student was quite simply like setting a variable to 2. I mean, this was the algorithm, right? And they saw that it had to have some sequencing, iteration, and selection. So what they did was they said, for I equals 1 to 1,000, x equal to 2. And then, if I is greater than or equal to 1, exit the loop. And they actually pointed out that that if statement was important because it kept the loop from going through multiple times. Right? So the if statement and the loop were there for only one reason, and that was to kind of tick off these boxes in the rubric. Okay. Unfortunately, or I should say fortunately, the rubric changed, and so now we no longer require those pieces. That wasn't the definition of an algorithm. So as a grader, I was very happy to say, sorry, kid, this is not an algorithm. You get 0 points. So be a little bit careful with playing to the rules, okay? Play to the spirit. It needs to be something interesting enough to call algorithm, okay? All right, 2D is about abstraction. So, I'm gonna go back. Okay, so what I want to do is I want to look at this quick algorithm here, just kind of to show you what it might look like. So this algorithm does collision detection, and the idea is that there is a worm-like robot. It's got 4 pieces that kind of can walk independently, right? But they're connected, and there's something that it might collide with, right? Maybe it's a log, whatever, right? So now the question is the robot colliding with something? Okay, so first part, lines 1 through 6, that is a loop, okay? That looks at each individual piece of the robot, there's 4 pieces of the robot, and checks the log that we're going against and tries to determine whether the log is actually intersecting that one piece. Now, how do we do that intersection? There's actually a magic routine here that this doesn't describe called seg to seg dist. It is the distance between 2 segments, I'm sure, okay? So it is the distance between the log and that particular piece of the robot. If that distance is smaller than the radius of either the log or the robot, then they've collided, okay? That's what this does. Notice that it's using seg to seg as part of the algorithm, seg to seg distance, or distance between 2 segments. That is the idea of having some other algorithm inside of it, okay? And then you have for I equals 1 to 4, that whole thing, that's kind of a piece. How can I describe it independently? It checks to see whether the robot is intersecting the log, right? That's what that piece does. If it is, then there's a collision, okay? Now, after that, we have lines 7 through 10. What that is actually doing is it's checking to see what the distance is between the first kind of link in the robot and the last link in the robot. Notice that the other ones in between can't be colliding, okay, because they're fixed, right? They're actually attached on both ends. But those other 2 could overlap. So we check to see if they overlap using the exact same seg to seg dist function, right? And if those overlap, then there's a collision. It's a self-collision, okay? So this algorithm actually has 2 parts. The part that checks for a collision against a fixed element, like a log, and the part that checks for a collision between the beginning and ending segment, right? It also has a 3rd part, which is the part that actually looks at 2 small segments and checks to see how far apart they are, right? The distance between 2 segments. That makes it a beautiful algorithm. It checks all of the boxes, right? It's got multiple pieces that make sense independently. What does this do? It finds the distance between 2 things. What does this do? It determines whether the first and the last element intersect. What does this do? It determines where any of the 4 elements intersects the fixed piece, right? And you can talk about it individually and together to be able to solve the bigger problem. Now, because it's complex enough, notice that it has math, it has if statements, it has loops. It almost comes with the territory, okay? You don't have to worry as much about that as long as it's a justifiable algorithm. So that's a good example of what we want to show. Okay, now let's look at abstraction, right? Your students have to identify a particular abstraction that they created in the program. So what do I mean by that? Perhaps your student is writing something that when you click the mouse, right, some function gets called and they write that function. So the actual software that they're using, this might be Snap, this might be Scratch, whatever, actually has an abstraction that whenever the mouse gets clicked, this function gets called. And the user just writes that function, the student writes that function. Well, they're not doing their own abstraction, right? The abstraction here could be something like key button pressed, right? They didn't do their own abstraction. They're simply completing somebody else's. That does not count, okay? Don't let them do that. They have to write their own. My litmus test is not the only way to pass this, but my litmus test is Write your own block, write your own function. That is an abstraction. Remember, it's an abstraction of code. You can also have abstractions of data, a list of students. That's a harder sell to the reader. So don't, right? Do the easy sale, and that's, I've wrote my own procedure. Definitely an abstraction, okay? You should identify the actual procedure as the abstraction, not the place that you call it, okay? Sometimes people make that mistake. It really helps if you call that procedure more than once, and here's why. Because part of the question is, explain how using this abstraction helped you manage the complexity of your program, okay? If there's a function or a block that you wrote and you call it from more than one place, then you can explain that very easily. See, I needed to do this in multiple places, and now there's only one call as opposed to copying that code over and over. Beautiful. That helps you reduce the complexity. Even if you can't claim that, you can always kind of argue something like, this is a self-contained process, and so it's nice to be able to put it aside, give it a name, and I don't have to think about everything that goes inside. So it reduces my cognitive load when I'm programming. Great, that's a good reason. Excuse, whatever. That's a good reason to use the abstraction. You can run with it, okay? But like I said, it's an easier sale if you can say, well, I called it from 3 different places, okay? Now, I want you again to look at this collision detection algorithm. Remember, we used the seg-to-seg distance function. Boom, abstraction, right? That was something, and by the way, I need it in 2 places. A link versus a log, and then a link versus another link, right? So it's great. It's a beautiful example of abstraction. The entire collision detection function is another abstraction, so you can use that one instead, okay? As long as you wrote a function, as long as you call it hopefully more than one place, you got an abstraction, okay? So that's what this does. Finally, there's prompt 3. Prompt 3 is just give me the source code. So Snap actually has a feature that says generate the source code as an image. So it just generates lots of files that have all the functions that you define and everything. And that's it. That's what you turn in, right? It's just the source code. You do have to do 2 things. First, you have to highlight the chosen algorithm. There's some algorithm that you said, this is the algorithm. Actually put an oval around it. Yes, it has to be an oval. You can't use a highlighter and highlight. No, it has to be an oval around it, okay? For your abstraction, you also have to highlight it. This time you have to put a rectangle around it. Rectangle for the abstraction, oval for the algorithm. Sorry, you just have to do that. That's the way it is, okay? Do not, like some students do, put a rectangle around the entire program. There's my abstraction. No. I believe you there's an abstraction in there someplace, but the student needs to actually tell me what it is, okay? The student needs to be the one that says, here's the abstraction, as opposed to let me say, well, I see that you abstracted over here, so I'll give you points. Not the way it works, okay? They have to be consciously doing an abstraction. So that's why they have to mark it. And with a rectangle for the abstraction, with an oval for the algorithm. They have to be conscious about that. Okay, again, I'm just going to briefly talk about feedback. Obviously, you have to give feedback to the students. They do need feedback to get it right. However, the rules are very clear. They cannot turn something in that they have received feedback on. So, ask them to write 2 programs. Yeah, right? Personally, I prefer to just do little pieces, right? So I may, for example, give them some code and say, identify the abstraction, okay? Or maybe I'll even identify the abstraction for them and say, explain why this abstraction helps to simplify the code, manage complexity. Those little activities are really good. And finally, taking a screencast, just have them do that as a homework early so they know what to do when they get to this stage.